Alright, in this video I am going to be making a spot welder like hundreds of other people on YouTube. But I thought I will just want to test a few things that most people do not test, and that is the current drawn by the primary at no load. So for now, I have wound a temporary secondary. Well, to do this test, you don't actually need the secondary in place. So I have removed the original secondary, but I did leave, and I'll try to show you here, I did leave the magnetic shunts inside the core. And okay, let's see if I could show that. And the magnetic shunts are these ones. You see there? Okay. That little plates there, sitting on top of the primary, they are the magnetic shunts. And the shunts, reason why they are called shunts is because they are blocking the magnetic flux that happens between the primary windings and the secondary. Okay? So, and that is because they are trying to control not this type of secondary, the original secondary, which I already removed, which is high voltage. They're trying to control the currents and voltage on the secondary in case of spikes, and which could cause the magnetron to go on short circuit, or the windings being damaged. So it's that's why they say they run these transformers for the microwaves. They run it saturated, which means it will limit the current of the secondary and also the primary, though the primary run a lot of current at idle. And of course in the microwave there's no idle, because either it's off or on. So when they apply power to the primary is when you got the microwave oven on, heating up something inside it. But if you had to run it without loading up the secondary, with the secondary being open, and you run the primary, it will draw about 2 amps. This is a 240 volt one here in Australia, okay, and 50 hertz. And I will show you that it will run 2 amps at no load. Okay, so I hooked up the power to it, but the power is still not on. And here I've got my variac, which allows me to bring up the voltage slowly. And you can see here so you can see the current 1.8. okay, so at around 240 volts, okay, it's actually over 500 watts, just an idle current. So it's taken 2.2 amps or 2 amps. Okay, and you can see the secondary is open, and there's no power generated on the secondary. And of course I have tested this in this way, and the windings at 2 amps still run very cold. So it doesn't actually heat up, but it does draw 2 amps. And And then I'm going to do a test in shorting out the secondary, okay, to see how much current I can generate, well, the transformer generates with these windings. So and with the shunts on will limit the high currents. Okay, it won't let the secondary take too much power, and therefore as well the primary will be limited as well, because then the whole transformer is already running saturated. So the magnetic field, the magnetic core, the flux of the magnetic fields is saturated. Therefore, it's like it hit its limit. Okay, so what I want to do here with the MOT transformer, the microwave oven transformer, I want to work out exactly what the exact ratio is to do a proper calculation of the current between the primary and the secondary. So at the stage I have the shunts still in there, and from the little bit of testing that I've done, I think I'm going to leave the shunts in there, because I am not after the full rating 100% for what I want to do with it. And I rather have the shunts because they do act like a bit of a regulator for the primary current, and of course it will affect the secondary current, but from the testing that I did, it's not actually affected by much. So the first thing I want to do again now to get a better calculation is to work out the ratio between primary and secondary voltages. So I am going to turn the voltage. So at the moment the secondary, it's got 3 turns and it's hooked up to the voltmeter, and that's going to be reading AC voltage. And let's put up the voltage to 240 volts. Okay, and you can see it's drawing just over 2 amps. Okay, so let's read the secondary voltage. This is saying it's 3.16. So check the primary, it's around 240. Okay, and I've got 3.16. So primary voltage is 240. I'll put this back here, and secondary voltage equals 3.16. Okay, so now if we divide, right, to get the ratio, 240 divided by 3.16 equals, and I'll get the calculator for that. And 240 divided by 3.16, 75.9. Okay, we can say it's 76. Okay, for short, 76. So ratio is 76 to 1. Okay, so that's the voltage. Now I want to work out the current. How efficient having the shunts is the secondary going to be? So I'm going to do a test and with this clamp meter. So let me put the voltage down. I am going to short out the secondary windings. And by the way, I can only do this because I've got a variac that can handle 8 amps. Otherwise, you cannot really do this test properly without overheating things and blowing fuses. So, as you can see there, I've got the primary hooked up to the variac there, and it's at 0 volts, and I'm going to set the current. Okay, now remember, this have an idle current of 2 amps. So technically 2 amps is being drawn, though 2 amps is only at 240. Okay, so if I do a test, actually let me do it properly. I want to do a test at 1 amps on the primary, and I want to see what the secondary is going to take. Now we can use the ratio that I've got here, 76 to 1. So let's do, hang on a minute. So up to, hang on. Okay, so up to 150 volts. Okay, 150 volts. I am drawing 350 milliamps. Okay, so I don't think I'm going to go over that voltage for this test. So I'm going to ignore the current this is drawing on the idle at this stage. Okay, so I'm going to draw 1 amp on the primary. Actually, let's make it easier and just go 3 amps. So, just to show you, I got 3 amps on the primary. There's the primary there. It's drawing 3 amps. I've got the secondary shorted. Okay. So according to the ratio, we're going to see what it's doing. So let's measure the current as it is. Let's go to the low scale. Be more accurate. Zero it. Overload. Okay, let's go. And according to this, I don't know why that's overload, because it says it can draw 600 amps. So I've got 211 amps secondary, and the primary 3 amps. Okay, 3 amps, 2.999. Okay, bring the voltage down. I've got 211. Okay, so let's see. So we'll write this down. Okay, so I had 3 amps on the primary, and the secondary I had 211 amps. Now, if we use the formula of the 76 to 1, okay, technically if I times the 3 times, sorry, yes, 3 times 76, the current should have been 228. So 228, I want to know the percentage here, minus 211 is 17. So 228 minus 211, okay, sorry, minus, equals 17. Okay? So, okay. So now I want to work out the percentage at this stage. So we do 17, okay, divided by 228. Okay, divided by 228 times 100. So times 100 is equals to 7.45% less. And that's probably because of the shunts. So at this stage, I've lost 7.45% at 3 amps at the primary. Okay. Now the voltage there was probably only around 60 volts. So I'm not going to take in consideration the idle current at the 60 volts because it's only in milliamps. So it's not even 1 amp. So that's that. Now I want to increase the current to a higher rating. So let's go at a current of 5 amps. And you can see we're drawing 5 amps, okay? On the primary. And what's the secondary saying? 355. Now I just want to double check this. Sorry. Make sure this is reading right. $352. Okay. Write it down. 350. It's going a bit less. That's because the wire is heating up and the resistance is going up. Okay. So that is why the current started higher. I think it was 355 and it's gone down to 352. And this wire is getting very warm. So it's heating up and the resistance is going high. So the current will reduce. That's okay because the voltage drop. Now, so before I had 7.45%. Now let's see. Let's do this calculation again. So 5 amps times 76, I said we're going to work. The ratio equals, that's amps, how much the secondary should be without any losses. Okay. So 5 times 76, 380. That's what we should have read, 380 amps. But I actually read 352 amps. Okay. Now, if we minus 380, 352, technically, right, I want to work it out at 355 because the wire started heating up because it was on for a long time. I want to see what that is. Minus 355 is 25 amps I lost. So then we do 25 divided by 380 divided by 380 times 100, 6.5. So the ratio now is 6.57% less. What was it before? Before it was 7. So at the lower current was 7.45. The higher I'm going with the current, the more efficient the secondary is becoming. So the shunts, looks like to me, that they're more effective at a lower current. At a higher current, the shunts are becoming less effective. Okay, so let's see. Almost 1% less. 1% less effective. Which tells you that's not a lot. I am not losing a lot by the shunts because we're only talking about 25 amps less at 5 amps on the primary. So what that tells me is that I actually done a research on Google, and they actually say that you can lose 30%. In this transformer, definitely that's not the case. So this particular transformer, definitely that's not happening. I'm only losing about 6 to 7% less current on the secondary, which again, for just to gain an extra 7% at a lower current and at a higher current, let's say 6%. And I know if I put more current, I'll do a last test, and I'll put, I'll try to boost it up to 7 amps or 8 amps, and I want to know what the secondary is. So I'll just do that. So we're still recording. That's 8 amps. Okay, 560 amps. Okay, 8 amps primary, and I got 560 amps on the secondary. Okay, so 8 amps primary, 560. Sorry, I wasn't showing that with the camera. So calculator. So let's go by the 6%. 560. I forgot the 0 there. That's amps. So let's see. Technically it should be, let's say if it's losing 6%, 560 times 6%. Sorry, 560 plus 6%. 593. So accordingly to that, let's say it was 6%, the secondary should have been 593 amps at 8 amps on the primary. Now let's see if that's true. 8 amps times 76 for the ratio equals, okay, so we do 8 times 76, 608 amps. So that's by 6%, right, of the 593. So let's do 593. 93. No, I'm lying. What am I saying? I actually read 560. So 560 plus, let's do 6.57%. Plus 6.57% equals 596.7. 596. So here the percentage is still a bit more, so maybe it's around the 7. So let's try the 7. 560 times 7%. 560 plus 7%. 599. Actually, I want to do this test again because I'm not convinced. I'm not convinced. 8 amps, yep. 582. 582 is what I read. That's because the wire is getting pretty hot here. So it's 582, you see? So let's start again. Sorry. With the formula, let's change this 582 at 8 amps. The longer I keep it, the wire is heating up, the resistance is going high, and therefore it's creating a voltage drop, which means the ratio is changing. So I'll have to measure the first current when I first start it while the wire is still cold. Okay, that's the true figure. So let's do so 8 amps by 76 of the ratio, we should get 608 amps on the secondary. Okay, and that is full efficiency. So now let's do 582 is what I've read on the secondary. So if I do 582 plus 6% equals 582 plus 6% equals 616. So now 92 amps. You see, as I said in the first place, the percentage is going down. So if I do, let's find out the ratio exactly now, the percentage. 608, which the full efficiency of that ratio, minus, okay, what I read, 582, is 26 amps is what I lost. Okay, so 26 amps divided, okay, 26 amps divided by what I should have read, 608 times 100 equals, for percentage, equals, 20, let's do it again, 26 divided by 608 times 100. It's 4.27%. So you see, the shunts, 4.27%. So the higher I go with the current, the less the less effective are the shunts, which means they are doing not much. At a certain current, the higher the current, as if like the shunts are not there. We're getting closer. So you see, I read 582 and I should have read 608. Okay, which is only 26 amps less. Therefore, how I said, I don't believe I need to remove the shunts. For the reason I'm actually going to use this transformer, and I don't like disturbing anything on the primary, because these shunts in there, they're epoxied in there, and there's not much insulation between the shunt and the primary. So, not to wreck the job, to me, I think this is going to do fine for what I want to use it. But I still prove the point that the information, now maybe it depends on some transformers. This probably was over 1,000 watt transformer. It's not a small transformer for the microwave. For high currents, something around 600 amps on the secondary, I'm only losing 4.27% of the efficiency. So that could be due to the shunts, and also, how I said, the wire at the stage is pretty hot. But anyway, I tried to compensate for that by having the readout of the current display straight away before leaving the wire heating up, and you get a not accurate reading, because you see, before I thought I measured 560 something when it was actually 582 at the 8 amps. So anyway, that's what I wanted to show there. Okay, hi. So regarding the spot welder that I'm building, I decided to try to make a box for it from aluminium sheet. Now, the problem with this is that I don't have a bender. So I tried to bend this on the vise with the hammer, and as you can see, it's got a lot of hammer marks and it comes very rough, and because the vise is not even as wide as this, and of course on some sections like this I couldn't really fit it properly in the vise because I don't have the depth. But I have come across an idea that I've tried, and I think it's going to work, and that is using my press. So I'll show you that. And that's the press, right? So this is the sheet that I had. Okay, I've cut the width, so this is going to be the top cover, and I thought, why not try to press it in there, which I did. So these are the steel plates that come with the press. Okay, these normally lay flat like that. Okay, you have two of them. So in this situation, it's laid like that, and what I did, I put the plate there after I marked it, and what I used is a piece of steel. This looks like it's 2.5 or 2 millimeter steel plate. I've marked where I was going to bend it, okay, in that format, and I pressed it down, and it actually has been pretty good. It's not exactly a 90, but the rest I'll sort of bend by hand. So now I'll have to line it up, and I'll mark it there, but let me just do that. Okay, so I've lined it up on my line, and I don't know if it's going to come exactly right, but we'll try it. So we're starting to bend. Let's see. Let me just double check it. Okay, I think it's coming not bad. Okay. All right, let's like that. And that's not bad. Now it's a matter of checking to see if it's the right size for the box that I did, the base. Okay, so here's the base, and this is going to be the top for it. It's still if I just check there, it probably did come a bit big. Not by a lot, but I still have to bend it a little bit more. Okay. I'll see how I go. Okay, it didn't come perfect, but it's not bad for this job. So it's only a spot welder that I'm probably hardly ever gonna use. It came slightly a bit big than it's supposed to be. Probably about 2 to 3 mil bigger. But from the back, it doesn't look that bad. But it would have been good if it had sharper corners. It was very hard to judge how on the press it was going to bend. So it's the first one that I ever did like this. So let me, yeah. Of course, I got to put make the front panel and some supports. But there it is. There you can see some gaps, right? But that's not bad. If I had a bender, metal bender, it would have been a different story. So anyway, continue on. Okay, this is what I got up to on the spot welder. Little project. And I've made the case. It's a bit rough. It's not perfect. It's got a lot of defects. Because you really need a bender to be bending this, but also I'm not that enthusiastic lately, so I've bent everything by hand and the press, but things don't come 100% perfect. So all these brackets here, it's all cut with the jigsaw from a flat plate, aluminium, and I bend it, pop rivet it. Okay, here. And so yeah, so everything's made by hand, a bit rough, how I said, and it's going to be screwed there to on the top, just to support these braces a bit better, and to there, and that's the back. I still have to drill where I'm going to run the power, and also I'm going to put fans. So here I'm going to have to cut a hole and put a fan, something like this. One there and one here. And the way I'm going to do it is one fan is going to blow the air in, okay, and it's going to mount something like that, okay. This will blow this way, and we're going to have the heatsink for the triac, which this is going to be mounted this way, and something like that. So I just put that there because I got to remove these pots. I'm not going to have the pots on the board. I have to install them on the front panel. Oh yeah, and I still have to make the front panel face. I haven't done that. But one fan is going to go there, so I got to make a bracket to hold the fan there, and the other fan is going to go at the back there. And there's going to be one at the back, one on the front. And this one at the back is going to suck the air out. And this one is going to blow the air in, so I can blow air onto the heatsink here for the triac, which I don't believe it's going to get that hot, but it probably will only be warm because it's only a spot welder. It's only going to be milliseconds on each time. And also the box here, I made it a bit higher than the transformer, so the heat is going to rise up, and with the fans that will suck the air out, and this will pump more air in. And the transformer to run the circuit board here, the controller, is going to be mounted something around there. Okay, I'll be honest with you, if I was going to be using this a lot, which I'm pretty sure I am not, I probably would have made my own circuit board just to have my own controller. Because if I had my own controller, I would have, instead of just having the milliseconds time and the cycles, sorry, the milliseconds is in cycles, and the percentage on the power, which is 33 or 30 to 99%, and that's what do you call it, phase angle shift. So that's what that's doing. I would have had an LCD screen, right, or another LED display to tell me the current. So the current will be estimated regarding, and I will be calibrating the percentage of the wherever the phase angle is at, and then I'll short circuit the leads of the output of the transformer and the secondary, and I measure the current, and I would have done some sort of calibration, and then I would have entered that into the software. So when I'm setting the percentage, I've got an idea of what current, and let's say you want 100 amps or 200 amps. That's going to stick in your mind, not a stick in your mind, but that's going to give you a better reference than percentage. But because I am probably hardly ever, I'm probably never going to use this thing. But if I was, I would do something like that. The other thing I can do is this has got a microcontroller here. I'm not sure if it's an SD type. I haven't programmed these before, but what I probably would have done as a test, I would have sacrificed, I'll remove this chip, and I'll use the rest of the circuit, and I'll put a PIC microcontroller in there, and I'll program it myself. And then I can, have the extra display or LCD screen. But anyway, I'll see how I feel one day. But the way things are going, I am losing a lot of will in doing these things. I don't feel well, so. But anyway, what else can I tell you? So yes, so that's pretty much it. And these, the output, I've got this other one here. It shows I've cut the wire. I'll have to remove that lug and fit it into there. And these are going to be something like this or like that. Okay, and the front panel. And I'll probably have a main switch here, a place where to put this, or one day if you replace that with an LCD screen, or and the knobs. Yeah, I probably as well, I would have made I mean, you can actually buy them as well, but again, it's not my software, so you can buy, like, instead of having a pot, you'll have a rotary controller. And the reason for that is because you don't want, by mistake, alter the, let's say, the cycles, and you'll end up ruining your job if you touch the pot or something goes wrong with it. So you're better off either switches or rotary switch to set the cycles and the current and the percentage. But I think the cycles is very important. So yeah, that's what I'm up to. And the things that I hate doing is drilling this big hole here for the fan. I could also, instead of drilling a big hole and putting that, you could put holes, but actually more work. And also, I only have one of these, and this is slightly big. For example, normally they have them the same size as that, as the fan there, but as you can see, it's a bit bigger. It doesn't matter because this will fit on there anyway. I can have its own screws. Plus, I was going to mount the fans on the case, on the cover, but then when you take the cover off, it will be a bit awkward. You gotta have a plug and unplug this. So I thought, since I've got the strap here, I'll just attach it to the strap like that. I'll make a bracket just to hold that there. And yes, it won't be 100% touching onto the face. Okay, I can put a little bit of foam there, but it's still going to work okay. Mainly it's going to get the air from the outside. And of course, these fans, you have to test them out because some of them, these are all actually made to suck the air out. And it's got they normally have a mark. Well, yeah, there you go. You see, it rotates this way and it goes from this way to that way. So you see, this is normally faces the outside. But so some of these don't blow a lot of air. They're good for sucking, but some of them, when you test them, they blow more air than the others. So it depends on the fan design. They're not all the same. These are pulled out from, power supplies, computer power supplies. And I have tested some of them. Some of them give out more air, blow more air than others. So it's all got to do with the fan design. Of course, these have a habit. They normally have a capacitor there, electrolytic, in the circuit, around 2.2 microfarad. Because these are very old, sometimes that goes and the fan won't run or runs a bit slower. The problem is you got to take this off. Take the clip off, remove the fan, and you got to be careful not to break the circuit board. To remove the circuit board, it's pressed in onto the housing where the bush is. But anyway, that's something else. Okay, that's it for now.